Okay, calculus. Today we're going to talk about our second derivative tests. And if you consider this graph here, if I draw a bunch of tangent lines, this represents the first derivative. I want you to watch what's happening to the first derivative. See how the first derivative is actually dropping? Like the tip of the tangent line is just dropping more and more and more. Kind of bottoms out there, and then it starts to head back up. So as we draw these tangent lines, you can see that they drop, 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 and then they head back up. And so as you see these tangent lines dropping as you move along the curve, and then all of a sudden they pick back up, that tells us that f prime is decreasing, which means f double prime is less than zero. It's f double prime is negative in that situation. And here where they're tilting back up, you can see that f prime is increasing. And what that means is that f double prime is greater than zero. We call this concave down. Concave down. And it would, if you dropped water on it, it would shed the water. Whereas we call this concave up. If you dropped water, it would hold water. This spot where concavity changes, it kind of flips from being down to all of a sudden coming up. We call this the inflection point. So concave up is where f double prime is greater than zero. Concave down is where f double prime is less than zero. The inflection point is where f double prime changes sign from positive to negative or negative to positive. Yesterday we talked about the local max happening where f prime changes from positive to negative. So if you consider your local max would be here, that's where you're concave down. So it also is true that f double prime is less than zero. We also talked about a local min being f prime going from negative to positive. If you look here, f prime is going from negative to positive, and you can see your concave up. So f double prime is going to be greater than zero. Sorry if I'm talking a little fast. This is the second time I've tried to create this video working from home with our day's events that we have going on today. So I apologize if you have to slow the video down at any point, but we're going to work through the second derivatives here. We know that the first derivative, f prime of x, was equal to x squared minus 4. And in your last set of notes, we talked about all the different characteristics of f prime of x is x squared minus 4. We're going to lay out now is f double prime of x, and that is equal to 2x. And so if you consider the graph of 2x, you can see that the graph is below the x-axis here. So that means it's concave up and concave down. It could be concave down from negative infinity to 0. That's an interval. It's going to be concave up here from 0 to infinity. And then we have our inflection point, and that is occurring at x is equal to 0. Now, one thing I'm going to do, I have one example on your worksheet as you continue to fill out these second derivative pieces where we actually start to map these points. If you were to, so these are intervals. This is a coordinate. An inflection point, it has a point, I'm going to write point, and the point is 0 for x, and we plug it into the original to get 2. So we know it goes through the coordinate 0, 2. Up here, we talked about local max and the local min. And the local max happened at an x value of negative 2 and a local min at an x value of 2. So we know that this has a point of negative 2 something and a point of 2 something. So the inflection point, the local max, and local mins, those are all coordinates. The other things are intervals. And if I type this function into my calculator and I go to my table, you see if I type in negative 2, I get 7.3. If I type in positive 2, I get negative 3.3. What that does is it gives me a really clear picture about how to graph this type of function. If I make a graph of 2, 4, 6, 8, 2, 4, 6, 8, 1, 2, 3, 4, 1, 2, 3, 4. See, I can plot 0, 2. I can plot -2, 7.3. And I can plot 2. Whoops, sorry, that point should be back here. Sorry about that. And we could plot 2, -3, 3.3. So something like about like this. And we know that it's concave down from -infinity to 0, so it's going to be concave down. That's my inflection point, and then it's concave up after that. So this gives a really good picture of what that graph looks like, knowing exactly how high and how low for our max and mins. So that's pretty cool, okay? So we'll move on to B. I've only got 15 minutes for this video, so I'm going to try to make sure I'm keeping good pace here. -4x cubed plus 4x, that was the first derivative. So the second derivative is equal to -12x squared plus 4. And if you factor out a -4, you can see you get 3x squared minus 1. And if you solve that equal to 0, 3x squared minus 1 is equal to 0, or 3x squared is equal to 1. Divide by 3, x squared is equal to 1/3. And then square root both sides. X is equal to plus or minus root of 3 over 3 when we rationalize that denominator. So what that tells us is this graph of the second derivative, as you look at the shape is in fact a parabola that's upside down. It goes through -root of 3 over 3 and through positive root of 3 over 3. There I have it. So when we're talking about concave up, concave down, and inflection, concave up is going to be from -root of 3 over 3 to positive root of 3 over 3. Concave down is going to happen here from -infinity to -root of 3 over 3, union with root of 3 over 3 to infinity. And then inflection happens wherever f double prime changes sign. So you can see it goes from negative to positive here, and it goes from positive to negative here. So inflection happens at x is equal to -root of 3 over 3, and x equals positive root of 3 over 3. So those are your two values where you have inflection. Now we could come up with coordinates like we did in the last one, but I'm not going to do that in this situation. But we are going to be moving on to actually sketching larger curves, and so we are going to need that skill in the future. Okay, the next one, we look at our derivative here. We have f prime of x is equal to 9 minus 9x squared over x squared plus 1 quantity squared. So that was from the other day. When we take the second derivative, we must use the quotient rule. The quotient rule says take the derivative of the top, which is -18x, times the bottom, x squared plus 1 quantity squared, minus the top, 9 minus 9x squared, times the derivative of the bottom. Chain rule for the derivative of the bottom, u squared, x squared plus 1. Derivative of u squared is 2u. Derivative of x squared plus 1 is 2x. We multiply those, we get 4x times x squared plus 1. All over x squared plus 1 quantity to the fourth power. Notice how all these have an x squared plus 1 factor. So therefore, when we get rid of it, it reduces accordingly. We multiply this through, we get negative 18x cubed minus 18x. We get minus 36x. Then we get a plus 36x squared. All over x squared plus 1 cubed. Negative 18x cubed plus 36x squared minus 54x all over x squared plus 1 cubed. And if I factor a negative 18x out of the top, notice I'm left with x squared plus or minus 2x plus 3 over x squared plus 1 cubed. Now, what does that tell us? Well, the bottom is always positive because x squared plus 1 is always positive. If we cube it, it won't change. Where is that guy equal to 0? If you used the quadratic formula, which many of you have plugged into your calculator already, made a video for you that last year. If you check out the quadratic formula, you'll find that you have 4 minus 12 gives you that negative 8. So there are no real solutions here. So this never crosses the x-axis. This thing right here, so this thing's always positive and this thing's always positive. So the only thing we got to be concerned about is this negative 18x guy. And I know what negative 18x looks like. It's a line that goes through 0. It starts positive, it drops to negative. It's positive here, it's negative here. So when we're talking about concave up, we're going to be looking at negative infinity to 0. And when we're looking at concave down, we're looking from 0 to infinity. And when we're looking at inflection, we're going to look at x is equal to 0. That's where it changes sign. So the point of this one was to talk about the nature of solving for this, as well as identifying that piece, that derivative. And finally, our last one, we found that f prime of x was equal to 4x minus 8 over 3x to the 2/3. Now, I would like to take a different, I don't like to use a quotient rule. If I just divide this, I get 4 over 3x to the 1/3 minus 8 over 3x to the negative 2/3. These expressions are equivalent. And when I write it like a power like that, then I can go ahead using f double prime of x. I could go ahead and take the derivative much easier way. I get 4 over 9 x to the negative 2/3, and then plus 16 over 9 x to the negative 5/3. If I write that out, I've got 4 over 9x to the 2/3 plus 16 over 9x to the 5/3. Notice that this 2/3 and 5/3, they differ by a factor of 1. So it's if I multiply top and bottom by x to the 3 over 3, notice I'll get x to the 5/3. So I've got 4x plus 16 over 9x to the 5/3 now. Now, as we test this to see what's going on, we have to consider where the top is 0, which is negative 4, and where the bottom is 0, which is 0. So if you plug in a negative, a negative to the 5th power is going to be negative. The cube root would be negative. So you're going to get a negative on the bottom here. But if you plug in, say, negative 5, you'd get a negative. Plug in a negative 1 on the top here, you get a positive and a positive. So you can see negative divided by negative will give you positive. Positive divided by negative is a negative. Positive divided by positive, positive. So therefore, it's concave up from negative infinity to negative 4, union 0 to infinity. And it's concave down from negative 4 to 0, with inflection points both here and here.